Many of you have probably heard the phrase, "you are made of star stuff," or "we come from the stars." These statements could not be more true. Countless great thinkers and average people alike have been inspired by the stars and space surrounding to do amazing things. Because of their contributions, we can understand how important the stars are today. Everything is made from atoms, including us. And without stars, we wouldn't have the variety and abundance of elements that we need to exist. Here I'll explain how the stars turn space dust into us. While I'm not an astronomer, I have dreamt of being one for a long time, and that led me to do a bunch of my own research and take multiple courses in astronomy and stars specifically. So today I'd like to be the one to explain the life cycle of stars. First, I'll talk about how stars form and how we categorize them. That will lead into the evolution of stars throughout their lives, the HR diagram, and how they relate. Thirdly, I'll go into what happens to different stars when they die. Every star is born from the interstellar medium, a cold, dark cloud of various gases, essentially. However, we mainly differentiate them based on their temperature and their brightness. In order to better understand how stars form, we need to understand the relationship between gravity, pressure, and heat. Gravity condenses our would-be star, rising the pressure. As that happens, atoms speed up and get hotter in the core of the star. With that covered, an interstellar space cloud begins to collapse under its own gravity and eventually break up into smaller pieces. These cloud fragments heat up as they shrink until they reach about 10 million degrees Kelvin at their small, dense core. When the young star reaches this point, nuclear fusion can begin. This is when hydrogen atoms, or protons, collide at such great speeds that they get stuck together like Velcro and create a whole new atom called helium. Nuclear fusion is a star's fuel source to help in its fight against gravity. In the process of this new helium atom's creation, an awful lot of energy is produced in the form of light and pressure. For roughly the next 30 million years, the star will continue to shrink, little by little, until the outward pressure of all these nuclei fusing is equivalent to the force of gravity holding the star together. Different masses of stars burn up their fuel sources at different rates. A fully fledged star is now born, and we can determine many aspects of how it will evolve based on its mass. While a high mass star has a lot of fuel to use throughout its lifetime, it generally has one of the shortest lifespans. This is because of the gravity, pressure, and heat relationship. It is high mass and therefore greatly affected by gravity. The higher temp that mass causes translates to a high rate of fusion, killing the star rather quickly, a couple 100 million years in total. By the same rule, small mass stars can live for trillions of years with their low rate of fusion. While mass is helpful for classifying stars in many cases, one of the main aspects we use is surface temperature. This data separates stars into their spectral classes. The spectral classes are as follows from hottest to coldest: O, B, A, F, G, K, and M. These unusual labels originated from an entirely different system of organization based on how much hydrogen a star contained. They went in alphabetical order, A having the most hydrogen and all the way down to P having the least. They took those same groups and placed them in order of temperature. The last method of classification to touch on is brightness, or luminosity. This is how brightly a star shines, and it's dependent on how much energy it produces. With the help of a little math, and if we know its temperature and its size, specifically its radius in this case, we can find its luminosity. Now that we know how stars are born and later categorized, we're better equipped to understand how stars evolve throughout their lifetimes and what the main sequence is. Stars are ever evolving throughout their lifetimes, and scientists have come up with a great way of tracking those changes. The Hertzsprung-Russell diagram is integral to astronomers and is a great way to track how a star changes as it ages. This is a Hertzsprung-Russell, or HR diagram. As you can see, it's split up into 4 different groups, A, B, C, and D. First, we're going to talk about Group A. This is our main sequence. This is where most stars will live out their adult lives. On this line, we see an expected trend where the top left stars are the hottest and most luminous, and the bottom right are the least of both. The surface temperatures range from about 40,000 degrees Kelvin to 2,000 degrees Kelvin. Group B stars are generally about 6,000 degrees Kelvin or less, here. But they're all more luminous than their same temperature counterparts on the main sequence. This is due to them all being far larger stars. With their greater surface area, they can do more with the energy they produce, so to speak, and appear brighter. These stars are called red giants. Group C, up a little farther on the chart, are yet again more luminous than the last group for the same reasons. These stars are the largest that we know of, termed the supergiants. A red supergiant, such as Betelgeuse, would extend beyond the orbit of Jupiter if it replaced the sun in our solar system. Group D, down in the lower left, are going to be the odd ducks in this case. We know that they're very hot yet very dim. The high energy, low luminosity mix tells us that this group of stars has a very small surface area. That, along with their coloration, gave them the name of white dwarfs. Many of them are so small that they're the size of Earth. Now, groups A, B, and C on the HR diagram are all considered to be living stars. What that means is that they have some form of nuclear fusion happening in their core. Group A, as the main sequence, are all fusing hydrogen into helium at their core. Once a star has fused all of its hydrogen into helium, it goes into a transitional state where it moves off the main sequence and has to find a new equilibrium between gravity and the energy produced in the core of the star. Since the star has no more hydrogen to burn, it begins to slowly shrink once again, continually increasing the pressure and temperature of the star's core until it reaches 100 million degrees Kelvin. Only then can it begin to fuse two helium nuclei together and start exerting energy from the core once more. As this goes on, helium becomes oxygen and carbon, and next those begin to fuse into a myriad of other elements like neon, progressively rising the temperature of the star. As this goes on, a tree ring effect is created in the star, where the center core is the hottest and producing the heaviest elements, as we see here in this chart. And in the surrounding rings, lighter elements are being produced. If a star is very massive, then eventually it will end up with an inert core of iron that it cannot fuse into heavier elements. The only stars that will get this far were born with 25 times the mass of our sun. The less massive stars will burn out somewhere along the way. When fusion is over, so is a star's life, but its death is not the end of its story. Now we understand how stars can create the elements necessary for life to form, but we need more than just elements floating in space to become living creatures. Here's how the death of stars will contribute to creating life. When a star is no longer creating new elements, it will first collapse, and from that point on, things get exciting. Since there's no longer enough energy being produced in the core of the star, it starts to collapse. The outer edges, where hydrogen is still being fused into helium, collapse first, and like dominoes, it incites the other layers to fall inward at about 70,000 meters per second. When it all hits the iron core in the center, it ricochets outward in a shockwave of energy, creating those heavier elements that a somewhat stable star could not. This all happens in just a few hours. Much of what made up the star is blasted out into space, leaving behind the collapsed core. The star now consists of two distinct parts at the center of a small, well-defined core of mostly ash, still very luminous. Well beyond the core lies an expanding cloud of dust and cool gas spread over roughly the size of our solar system. This is called a planetary nebula. The expanded cloud, once fully separated, floats about in space, ready to once again join a dust cloud and become a new star. As the surrounding nebula recedes, we can now see what remains of the star is what is called a white dwarf. This is group D on our HR diagram, and this is the result of gravity winning, per se. It is extremely dense and still very hot. However, over time, this star remnant will begin to cool off. It will shift from white to yellow to orange and then red. Eventually, it stops glowing at all. At this stage, the star is termed a black dwarf. This is the ending for many, many stars, all less than 25 solar masses. Those over that mass will eventually come to make iron in their core. These stars go through a similar yet far more violent and energetic explosion to separate its core from its floating gas cloud. This is called a supernova. The would-be white dwarf core of the star can in some cases become what's called a neutron star. They're a rare phenomenon, more massive than our sun, but not hot enough to fuse elements in a way that could fight gravity. This neutron star is also about the diameter of Sacramento. The density is so immense that it's been pushed to the physical limit. The only reason it can't condense any further is because two atoms would have to then occupy the same space. The neutron core should be as dense as it can possibly become, but because there's something even more dense than this, we know that that's not true. The mass of a neutron core can be up to 3 times the mass of the sun. After that point, the laws of physics change. This is when black holes are created. They're neutron stars that have exceeded 3 solar masses. Atoms are shoved together as this is an extreme condition. This was the size of a large city, but it could now possibly be smaller than a thumbtack. Black holes and neutron stars alike attract matter and join with it to continually find mass where they can. Matter will orbit the black hole before it is merged, and this is a phenomenon that scientists can observe as closely as in our own galaxy, at the very center to be precise. At the center of every known galaxy, in fact, is a supermassive black hole that the galaxy orbits around. The less is known about objects and phenomena, the larger the scale that is being studied. But we do know that these supermassive black holes have a supermassive effect on gravity surrounding it. It gathered enough matter for a galaxy full of stars and planets to form. And they formed right where it needed to be for life to flourish. Astronomy is an entire field of study in science, so of course there's far more depth and detail to stars. However, everything that was explained today gives a pretty good understanding of how stars live and die, along with an understanding of how they created the necessary conditions and elements for life. Thank you for listening and coming to know how we're made of